Okay, the next technique we will talk about in terms of number of particles. Previously, we talked about the crystal size of distribution. But in crystallization, we also include the nucleation and growth. Growth means the crystal grow to a larger size from smaller size to be the larger size. But beginning mechanism we call the nucleation. Nucleation means the generation of the crystal. Because I talked to you at the earlier, the crystal is generated from the clear solution. That's right. The clear solution, the kinetic that the crystal generated from the clear solution, we call it the nucleation. The nucleation that means we consider in terms of number of crystal. That's right. Number of crystal. Okay, in this slide, we show you how to study the number. Okay, from the previous, we talk about the size in terms of mass distribution. We can convert the mass distribution to be the number distribution by equation 6. Equation 6 number distribution in terms of number crystal number density or the population density. That's right. Delta n is delta m. That's right. The mass in its length divided by the mass that we talk to you, low kV L average power 3. Low is the density of the crystal. kV is the shape factor of the crystal. L average is the average length of the crystal. And then you can calculate the delta. And then you can calculate the crystal population density or crystal number density by divided this by delta L. That's right. In similar way with the previous. That's right. We divided delta W by delta L. That's right. You get the crystal size distribution. But for this case, you divide delta N by delta L. You get the population density. That's right. Population density. The crystal density or the number density, the unit is per liter or per volume. That's right. The typical is per millimeter, per micrometer, something like this. This is the unit. Okay, sorry, this is for the dimension of n. That's right. N is defined by equation. This is n and s. The unit should be per length. That's right. It's per length. Okay, it may be, but sometimes usually we define in terms of millimeters per millimeter per liter. The number, that's right. The number it should be number per millimeter per liter, something like this for the unit of this. Okay, I will show you the example. Sorry. Like from the previous. Okay. Okay, for this example, I would like to calculate the number density. Salicylic acid crystal are how from magma. I think you know magma. Magma in the slurry, that's right, or the mixture of solution and crystal. That's right. The density of this slurry is 120 grams per liter. That's right. After crystallization, the crystal are washed dry. That's right. And size fractionated by size fractionation means the detonation or measure the size distribution by sifting. That's right. By the previous technique. The mass fraction of crystal retained on the seed between 210 250 is 0.14. This is the mass that retained between these two sides of the seed. Right. The density of crystal is 1.44 grams per cubic centimeter. And also we know the shape volume shape factor, we know kV. Right. We know kV, we know density. That's right. The question is, what is the population density of the size of 230? This is the average length. That's right, average length. It's between this. This is the average length. Okay, you know L average, you know kV, you know low. That's right, you know density. You know the mass retained. That's right. You can calculate crystal number density. You can calculate crystal population density. Like this, for example. Okay, for this case, the average. Okay, the average between 210. That's right, 210, not 201. 210, 250. You get 210. 30 micrometer, and then you calculate, right, sorry, delta M, right, delta M, and delta N is delta M over delta L divided by rho KVL over 3. This is delta M, right? This is delta L, right? This is the density. Okay, sorry, this is not density. 120. What is the 120? This is the density of the magma aside. Okay, we multiply the density of magma. Okay, density of magma. This is the law of crystal. This is the KV. This is the L average aside. This is the unit conversion. We convert micrometer to centimeter, like this, centimeter to micrometer, and then you get N equal to 4.4 multiplied 10 power 4 micro per micrometer per liter, like 4 microliter per liter. And also you can convert from the liter and micrometer in the same unit line in the length meter. You know, right? 1 cubic meter equal to 1,000 liter. You know, 1 meter equal to 10 power 6 micrometer. You get this. So this is the crystal density distribution. So you can convert from the size to number. You can convert the number to the size by using this converter, low KVL power 3. You can use this to convert from the number to size, from the size to the number. Okay, this is the technique to analyze the particle size distribution or crystal size distribution. And another term that we need to know about the crystal, because the crystal is the purified product. It's the purified product. The purity is very important to know. The purity is very important to know. And the purity of the crystal is very, very high. It's 99.5%, up to 100. Up to 100. Okay, but sometimes, why it's not pure? But sometimes there is some absorption or desorption of impurity on the crystal surface. It may be the impurity on the crystal surface. Okay, how to remove this? You can remove by watching, and then you can recover by filtration or centrifugation. This is easy to manage. But if the crystal entrap of water liquor between crystal forming accumulate, for this case, how to reduce the impurity by the water or the matter liquor entrapped in the crystal. For this case, it can manage or it can solve by manipulate the condition for crystallization. And we talk to you later how to crystallize. Okay. And sorry, and also the inclusion of small quantity of the water liquor within crystal. For this case, it's very, very difficult because the water liquor include in the crystal structure. That's right. In the crystal structure. For this case, it's difficult. You have to solve this by minimize the rate of crystal growth for that case. And also this is the including of the impurity in the molecule of the crystal. That's right. In the molecule of crystal, for this case, it's the difficulty also. You can solve this by recrystallization. That means after you produce the crystal, you can resolve or dissolve the crystal in the solution again and crystallize it. This is the technique to do the purify, because the impurity can be attached on the surface of the crystal. As I attach on the surface of the crystal, or the water liquor attract between the crystal forming. That's right. The crystal forming. There are many the solution attached on the agglomeration. Agglomeration means the crystal is mixed together. That's like co-together. That sometimes liquid inside this. You can solve this by reducing the crystallization. That's right. And also there are sometimes the water liquor inside the crystal. Okay, for this case, you can solve by the crystal growth technique by minimizing the rate of crystal growth. And the last problem, the molecular molecule, we talk in the molecule, that's right. The molecule of the impurity include in the crystal structure of the crystalline phase. This is also inside the crystal structure. We cannot solve this by adjust the condition by watching aside by the condition. For this case, you have to crystallize again. Crystallize again for that case. This is the difficulty technique, difficulty the problem that we have to solve. Only recrystallization. Recrystallization means crystallization again. That's right. This is the impurity possible in 4 ways. And also you can calculate impurity, like the purity of the product by this equation. Like for example, you can calculate by weight of solute in crystal cake divided by weight of solute in the filtrate. Or you can calculate impurity by weight of impurity in crystal and impurity in the filtrate. After you filter, that's right. The purity can remove by filter. That's right. Can remove the filter. Okay, and then you can calculate the separation factor by the ratio of EA and EB. EA is maybe the desired crystal. B is maybe the impurity, like that. Beta should be greater than what you prefer because you prefer A. Okay, like for this example, I calculate the purity factor. We have a mixture of sigmoterol and citroterol, right, weighing 2040 kilograms. And then we divide it into fractions. So the original mixture contains 86.5% sigmoterol. And then you can recover the crystal of this by 96.6%. So the weight is 1,137. Okay, the solid in liquid contain 74.6% sigmoterol. And found how to determine this. We determine it by the evaporation to dryness. That's right, evaporation to dryness. What does it mean, evaporation to dryness? We dry the solid by evaporation technique. That's right, evaporation the solvent out, evaporation the water out from the surface of the crystal. So for this case, you can calculate the beta by estimate the E sigmoterol and E, what is the next one? Citroterol. That's right, like EA, EB, something like this. And then you get E sigmoterol is 1.36, 1.63, and E citroterol is 0. You can see that the ratio of 1 divided by 0. Something like this, you get approach to 10. Beta is quite very high. That means you can separate sigmoterol. That's right, you get pure sigmoterol by this technique. And another technique that we can use to purify or identify the purity of the crystal. This is the high technology, or the first example that we have in the HUT, something like this. We use the X-ray technique. That's right, X-ray technique. We use the XRPD, this for X-ray powder detection. We use it to detect the crystal, to detect the chemical. It's pure or not pure. That's right, it's pure or not pure. For this case, we have 2 forms of diamethylene, from gamma and from alpha. This is the peak of form gamma, pure gamma. That's right, pure gamma. You can detect by what is the different peak. Okay, for pure gamma, we have this peak. Right, there is no this. Okay, we can conduct this is the pure gamma, 100% gamma. And how to detect the pure alpha? You can see that pure alpha. Pure alpha, we have this peak. That's right, there's no peak for that. You have to find what is the peak that is the characteristic of its crystal. Okay, you can identify. If you have the sample and then you check the X-ray, right? If you have both peak, this peak and this peak, you can conclude that this is not pure. That's right. It's mixture between alpha and gamma. That's right. It's only this peak, not this peak. Okay, you can conclude that this is pure alpha. If it's only this peak but not this peak, okay, you can conclude that this is pure gamma. Like this is the X-ray technique. X-ray, and another we use the Raman spectroscopy. Raman spectroscopy. I will new one from my lab. This is the next one. This is the Raman. For this case, if we PLA, that's right. We check the peak, the same peak, same. But PLA, there is no this peak, that's right. And there is the small or the lower peak, that's right. This is the PLA. And PLB, we have this peak and the higher peak of this. That's right. At the mixture, we have both of this peak, both of this peak, both peak. The peak will show you the chemical is pure or not pure. But for this case, we talk in crystal or in the solid form. In the solid form, right? Okay. And also we can use the DSC, differential scanning calorimetry. That's right. This is the thermal technique. For this case, we detect the melting point of the solid. That's right. Different solids, different chemical, different melting point. That's right. This melting point. You can see that alpha and gamma. Alpha and gamma is different peak of X-ray. This form B and form A is different in Raman, and also alpha and gamma is different in the melting point. The melting point is the highest peak. This melting point allow this. This melting point allow this. That's right. The melting point of the crystal of different form and of different chemical or different melting point. But you can identify the purity by DSC. How about if we have the mixed crystal, right? If we have both alpha and gamma, you can see that the peak of what we have two peaks of this. This may be two peaks like this. This is also one peak for gamma, one peak for alpha. Like this. If we have both, that's right. We have mixed alpha and gamma. The DSC will show both peaks. That's right. With all okay, you can define this mixture. This is pure, like this. Okay. And also by the, you can use another technique. We call this is the ATS state. That's right, ATS state. Like this, we check the lysozyme. Right, sample 4, sample 5, this is 5 to 9 is the pure lysozyme. This is not pure. Why it's not pure? Because we have a lot of peak around this. That's right. ATS state show the size in the molecule like kilodalton. We detect the size of the molecule because the size of the lysozyme is in this, but for this sample is a lot of protein. That's why it's maybe lysozyme, albumin, and atom. And also for this is the mixture. We have a lot of peak, but sample 4 and 5 is pure lysozyme, only one. Okay, this is the technique that I talked to you, how to identify what is pure or not pure. That's right. How the technique we can use the high technology like X-ray, Raman, DSC, ATSP can apply for determine the purity of the crystal, or you can determine what chemical in the system. That's right. We can use this to detect what is the chemical in the what is the element that's found in your chemical. It would like to detect the atmospheric air pollution. You can check like this. There are many techniques in the equipment building of HUT. In my lab, we have the Raman, and we can use for the central equipment building like X-ray, DSC, something like this. Okay, for the next topic, we will focus on the kinetic or mechanism of crystallization. So previously we talked about the important term like crystal size, purity technique, the polymorphism. And the next topic, we will focus on the kinetic or mechanism of crystallization. Before we talk the mechanism, we introduce you about the important term like supersaturation. The crystallization will be occur if we generate the supersaturation. That's right. The critical phenomena in crystallization process are the formation of new crystal and crystal growth. This is a nucleation kinetic. That's why the new crystal occur. The growth means the crystal grow to the larger size. That's increase in the size from smaller size to the bigger size. The new crystal form nucleation. This is the generation of crystal from the clear solution. This kind of thing. And also how to determine the particle size, how to determine the number of crystals. We can correlate with the N and M. That's that we talk to you. Particle size distribution, number density distribution, size distribution. Okay. The driving force to induce the crystallization, we call the supersaturation. That's right. We call the supersaturation. It's the driving force. The supersaturation means the solubility or the concentration far from the solubility. The concentration should be higher than solubility. That's right. And the solubility, what is solubility? Solubility is the maximum. That's right. The maximum concentration of solute that can be dissolved in the solvent at condition of temperature and pressure. Now, if you would like to crystallize the sugar, that's right, the crystallize the sugar, the concentration of sugar should be higher than solubility. That's right, should be higher than solubility. The solubility depends on temperature and pressure. Right. Okay, for this case. The solubility, sometimes we call this is saturated condition or saturated solution. We cannot crystallize when you start from the saturated solution. That's right, at 25 Celsius, we have only one concentration of the sugar can be dissolved in water. That's right. At higher concentration, we cannot solve. That's right. At lower concentration, we can dissolve sugar faster, like this. We call it the saturation. If the concentration is higher than saturated, we call this is the supersaturated solution. That's right. If the concentration is lower than the concentration at equilibrium or at saturated solution, we call undersaturation. I will show you this. Okay. This is I talk to you. This I show you the phase diagram or the solubility data, temperature, and concentration of the solute dissolved in solution. And we talk it at constant pressure. Constant pressure. That's right. Okay. This is the solubility curve. For example, at this temperature, right, T1, only the solute can dissolve in this solution at this point. Only this. That's right. Only this. And also at this temperature, only concentration. This is the concentration that can be dissolved. It's the maximum. This is the solubility. That's right. The zone that's under the solubility we call the undersap. That's right, undersap. If you start from this zone, you can add solute, and then you can dissolve faster until it's the maximum. Right, this is the maximum. How about this zone? This zone above the solubility line, you call the supersaturation zone. Right. Supersaturation zone. But we separate the supersaturation into zones. Metastable zone and labile zone. That's right. Metastable zone and labile zone. The metastable zone is the lower concentration, but also supersaturated. For labile zone, it's higher solution. That's right. Higher supersat. The labile zone most is nucleation. That's right. This is the nucleation mechanism. The clear solution will generate a new crystal at this region. That's right. At this region. But it cannot generate the new crystal at this region. Because this region, the concentration is quite low and the driving force is quite low. That's why the driving force means the difference in concentration and and solubility. That's right. We can talk in supersaturation, we can talk in the delta C. Okay, let me talk. Okay. Right. For this region, crystallization is not possible. That's right. In this region, mode we operate by the crystal speed. We have the crystal in the system already. For this case, we use to control the particle size. This is the most common found in industry. Right. We will operate in this region. If you would like to get the uniform inside, you operate in this region. If you operate in this region, you will get many size. The size is quite different. How to do that? You operate in this region first, and then you cut the size, and then you operate in this region while you feed the size, something like this. Okay, for example, if we would like to crystallize, okay, you start from point A. You start from point A. It's many dogs around my house. Okay. We will start from point A. What is point A? Point A is the undersaturated solution. That's right, undersaturated region. For this case, if you start from point A, you can add more solid. That's right, and then it dissolves. But for this case, we have no do that. We only decrease in temperature. If you decrease in temperature from point A to point B, that's right. The point A is under sap, but point B is sap. That's right. Okay, from this case only decrease in temperature, but concentration is constant. Okay, from T1 to T2, right? T2 is lower than T1. Okay, for this case, from the under sap to be sap. That's right. You can change from under sap to be sap by change in temperature by reduce the temperature. Okay, if you reduce the temperature further, it's maybe around this. TT means the solution at supersat. That's right. This is a supersat already in the metastable region. And if you reduce further to point B, it should be 3-4. At T4 concentration is supersat also. That's right. But this is higher than the metastable zone. That means you can generate the crystal spontaneously for that case. That's right. For this case, the crystal can generate spontaneously. When the crystal generates, the solution concentration is reduced also. If it reduced in this term, you can get this is the particle size or crystal go to the larger size. As I did we call the cooling crystallization. You can crystallize by cooling technique. As I by cool the temperature from point A to point B and point B to point B, you get the crystal. Right. If you cool to point B, there is no crystal. That's right. If you cool in this zone, there is no crystal. That's right. There is no crystal because it's quite low. But if you cool to point B, okay, you get the new crystal because this is the supersaturation is nearby zone. That's right. If you would like to control the particle size with no nucleation, you only cool to this side. That's right. If you cool the solution to this side, there is no crystal. But if you would like to control the size, you can feed the solid to the solution in this. So you feed the solid side in this side, and then the solid that you feed will be grow in the larger size. From the smaller size to be the larger size. You have to do by this. So it's the technique to control the particle size to check the size of the particle. This is the example for the crystallization by cooling. By cooling, that's right. Okay, another technique that we would like to crystallization we call the evaporation. Evaporation filterization. What is it to increase the concentration by evaporate the solvent? For this case, we do not increase the concentration. We only reduce the temperature. That's why we change from undersat to sat to supersat. We generate the supersat by cooling. But for evaporation, we generate the evaporation by we generate the supersaturation by evaporation. You evaporate solvent out. When the solvent is reduced, solution volume, that's right. Solution volume also reduced. When the solution volume also reduced, concentration increase. That's right. When the concentration increase, if the concentration increase to the supersaturation, it's okay, we will get the generation. This is the evaporation technique. Evaporation technique. Like you produce the salt or sodium chloride. That's right, salt or sodium chloride by evaporation technique. You can produce the sugar by evaporation technique, or you can produce the sugar by cooling crystallization. This is the basic mechanism for crystallization by two types: evaporation and cooling. That's right, the cooling evaporation. But the concept for the crystallization is how to generate the superset. For this case, we generate the superset by cooling. We can generate the superset by evaporation or by precipitant, the same as the precipitation. That's the generation, the supersaturation by adding some chemical, like the precipitant. That's also the crystallization, but at very high superset for the precipitation. Okay, I give you two types of the basic crystallization technique. There are more than this time. I will show you in the next week about evaporation, cooling, and high solvent, reactive crystallization, salting in, salting out. Also, there are lots of types of the crystallization. Okay, what is the driving force for the crystallization? We call that the supersaturation. We can define in at least three types of supersaturation or driving force. You can define in the concentration different. Concentration different. Delta C equal to C minus C star. C means the actual concentration. C star means the saturated concentration or solubility. C star is solubility. Okay. And it's maybe you can express the term of supersaturation ratio, right? S, C over C star. If the crystallization can be crystallized, delta C should be greater than 0. H should be greater than 1. That's right. Should greater than 1. If it equal to 1, C equal to C star, there is no crystallization. If C minus C star is equal to 0, there is no crystallization because it's saturation. That's right. It's saturation. If C minus C star is minus value, it means no crystallization because it's under saturation. C divided C star is less than 1. It's also impossible because it's under set. That's right. Equal to 1 means set. Less than 1 means under set. And also you can express in terms of relative supersaturation. C minus C star divided by C star. That's right. Or S minus 1. For this case, it should be greater than 0. That's right. It should be greater than 0. Okay, this is the definition of supersaturation in terms of driving force, in terms of the ratio, in terms of relative supersaturation. I did give you some example of the solubility. That's I did example of sodium chloride, potassium nitrate, sodium sulfate. You can see that like this is the potassium nitrate is the strong increase in increase in concentration with temperature. That's right. If you increase temperature, solubility is increased. This is the solubility of potassium nitrate dissolved in 100 grams of water. If we talk about the sodium chloride solubility is quite constant. That's right. It slightly depend on the temperature, and also sodium sulfate. That's right. Sodium sulfate at lower temperature than 40. Solubility is strong, increase with temperature, but at higher than 40, solubility is slightly decreased with temperature. That's right. This is the effect of scale. That's right, scale. Okay. There are some when you operate, when you have some salt in the stream of water in industry. That's right. If the temperature is higher than 40, it may be the crystal accumulate on the surface. This is effect to the equipment in the industry. Is very, very important problem when you work in industry. We call it the scaling. That's right, scaling. In Thai, that's right. What is Cambodia? I'm not sure. Okay, this is the problem based on the solubility data. And also another example, right, for this is the example of solubility of citric acid, glutamic acid. Like this citric acid quite strong, depend on temperature, and also like glutamic acid with amino acid. In terms of sodium glutamate, in terms of sodium hydrochloric acid, glutamic acid. It's also most of this strong that depend on the temperature, strongly depend on the temperature. And this is the example of the methionine from my paper. Methionine is also strongly depend on temperature and also strongly depend on the additive. For this case, we have three types: methanol and water. That's right. And also methionine. We have three components. Methionine dissolved in pure water, methionine dissolved in pure methanol, and methionine dissolved in mixture of methanol and water. We call this is the technique of anti-solvent crystallization. Anti-solvent crystallization. At the originally, we have water and methionine dissolved together, and then we add methanol. If you add methanol to this mixture, the solubility of methanol in water will decrease. Because the methanol and water is light together. It's water like methanol. It's easy to dissolve methanol and water, and then the solubility of methionine is lower. You can produce more and more crystal by this technique. We call the anti-solvent crystallization. Okay. This the next example, like the solubility of cycloxanine, that's right, amoxicillin, something like this. It's also the pH effect. So this is the pH effect, and also this is isoelectric point, something like this. At the minimum solubility, you can operate the crystallization or precipitation. For the case, you can operate by adjust pH. That's right, adjust pH. This is the solubility of glutamic acid change with pH. That's right. And also, I talked to you, the solubility depends on pressure, depend on pH, depend on the temperature, depend on the solvent that you use. Many factors that affect the solubility, and also many factors affect the crystallization. You can crystallize by adjust this pH, by adjust temperature, by adjust pressure, by change the entire solvent, by change the solvent. Right. Like for this, give you some basic example for the basic mass balance. I think the mass balance that we study from the PCE, print chemical engineering, is very important. Okay, for this case, we start from 10 kilograms of adipic acid. That's the adipic acid. It's really in 13.1 kilogram of water. And for this solution, we heat up to 90 degrees Celsius. That's right. We heat the temperature to 90 Celsius to dissolve all the solid. That's right. To solubilize or dissolve the solid. Okay, and then this solution is filtered to remove insoluble impurity. That's right. We filter the solution to remove some impurity. Okay. During heating and filtration, 10% of water is evaporated. That's right. 10% of water is evaporated. We initially mix 10 kilograms of adipic acid and 13.1 kilograms of water, and then we heat up from room temperature to 90 and filter, and we found that 10% of water evaporated. That's right. 10% of 13.1 kilograms of water evaporated, and then we get the clarified solution. The clarified solution will be obtained from the filtration. Okay, then we cool this solution to 35 Celsius. We cool to 35 Celsius and filtrate again. That's right, and filter again. Okay, at this temperature, the solubility is 0.05 kilogram adipic acid per kilogram water. This is solubility. That's right. This is the solubility at. This is the solubility at 35 Celsius. Right. This is the C star at this temperature. Okay, the question: how many weight of the crystal recover in this operation? How many weight of crystal? That's right. After we cooling from 90 to 35. Okay, for this case, we can apply the mass balance for water, mass balance for crystal to solve this problem. For example, for this case, we look at the general mass balance equation: input minus output plus generation minus consumption equal to accumulation. I think you know this is there is no chemical reaction. There is no generation, there is no consumption. And also we assume like the flow of the fluid and solid input and output is the same or continuously. We operate continuously. We consider steady state. Okay, there is no change, no con, and no accumulation. Finally, we get input equal to output. So, okay, if we balance on water input equal to water out, but water out by 2 streams. Water out in water liter and water out by evaporation. Because we have 10% of water evaporate. Okay, we know the water in is 13.1 kilogram. We don't know the water out. That's right. We know the 10% of water evaporate. Okay, 10% means 0.1 multiplied the feed is 13.1. And then you can solve for water out. Water out is 11.79 kilogram. Okay, you know the water. Okay, the second balance, you can balance on solute or adipic acid. Adipic acid. Okay, initially the solute in solution, weight of solute in equal to weight of solute crystal out, and weight of solute remain in the solution. This is very important point of view, because after you crystallize, we have a mixture of solid and liquid. Solid means the crystal of adipic acid, but liquid in contain 2 components in liquid surface. In liquid contain solvent and solute. The solvent is water, solute means adipic acid, but this is liquid phase. That means the adipic acid dissolved in water. Okay, the adipic acid we have 2 streams and output in liquid phase and in solid phase. In solid phase is pure form. Okay, for this case we know initial feed adipic acid 10 kilogram. We don't know the solid of crystal after crystallize. That's right, but we know the amount of adipic acid dissolved in water at what temperature? At 33, because we crystallize at 33. Because you know the solubility. At 33 Celsius, we know 1 kilogram water includes 0.05 kilogram adipic acid. This is the concentration. Okay, we get 0.05 multiplied by 11.9, 0.79. What is this? This is the water. That's right. This is water. Okay. Because the 0.05 is the kilogram of adipic acid per kilogram of water. You multiply by the kilogram of water, you get kilogram of adipic acid. That's right. And then you can solve for weight of solute in the crystal. Okay. Finally, you can calculate amount of crystal. That's right. Amount of crystal is 9.41 kilogram. The initial is 10, but you can crystallize is 9.41 kilogram. This is the basic example. But on the next week, I will talk to you the balance. I think I talked to you in the principle of chemical engineering already, and I will talk this again. How to apply the mass balance for the crystallization operation.